All right, everyone, welcome to the set theory seminar. Our speaker today is Monroe Eskew from the University of Vienna, and we'd still like to believe exists the Kurt Research Center. And he will talk about integration with filters. Monroe, go ahead.
Thank you very much for the invitation. So I'm going to talk about a current project that's joined with Emanuela Bottazzi. I want to give the following disclaimer, which is that there, first of all, is not a whole lot of set theory here. I mean, there's some at the end, but it should be fun nonetheless. And it's also kind of a bit out of my, well, it's definitely out of my usual research focus. So, and it's a work in progress. So, if anything appears a little naive or something to those who are a bit more experienced in non-standard analysis, just feel free to offer some suggestions. But let's get started. So, okay, so to try to make this sound really fancy and important, I'm going to talk about physics. So Feynman introduced what's known as the path integral, and this is a kind of a description of an integral. And I honestly don't know. I mean, I've never like done this stuff with lots of computations, but from what I know, it's a bit informal, and the idea is you have like a particle that can travel from point A to point B, and there's some randomness that determines the exact path. And to compute what will happen, to make some predictions empirically, he wanted to average over all possible paths. And so there's infinitely many paths, but moreover, if you try to describe it as a space, it's infinite dimensional. So it's not obvious how to do this, but he said, okay, we'll take an integral where the variable of integration is the path. And so you're in some kind of function space. And from what I understand, there are various ways of people have spelled out what it means formally in certain contexts, but apparently there's no kind of general treatment of the idea that's mathematically rigorous. Now, if you disagree with this, then let me know. But this is a quote from a recent article in the Quantum magazine describing the kind of basic issue, which is that there's no known mathematical procedure that can meaningfully average an infinite number of objects covering an infinite expanse of space in general. The path integral is more of a physics philosophy than an exact mathematical recipe. So one way of motivating what I'm going to introduce is that it is in some sense like a general procedure for averaging arbitrary number of things given certain algebraic structure. So, okay, I would like to say there's another well-known way in which you can do this, which is the ideas of the basic setup for non-standard analysis. So here's what you can do. Let's say you have a set X, and to just put it in the most general context, you have a divisible abelian group G. So divisible meaning it's this kind of thing where you can, and abelian, so you can add up things where order doesn't matter, and you can divide by the number of things you have. So averages make sense. So suppose you have an elementary embedding from V to M. Of course, this doesn't have to be the full universe, but just simplify things. You have this, and in M, you have a set that covers the image of X that M believes is finite. Then, working in M, you can compute for any function from F to G, you can average the image of this function over all the points in the covering set that's finite. This will give you an element of J of your group. And since it covers X, this is in a sense, this is some sense of averaging over everything in X. So all you needed was that, taking finite averages makes sense, and you go to some context in which the entirety of the points that you have in the space is seen as a finite set or covered by a finite set. Okay, and then after you do this, let's say maybe your group was the real numbers. So it's a ordered field, and we can extract something more concrete, which is the standard part. So an element of the J of the reals would be, you can take the standard part of it by the what's written there, the soup of the rationals, which are definable subset. I mean, definable point-wise that are below the given element. So this is the standard part of X, and there's a representation theorem of Henson from the 70s, which says that every measure space, like every probability space, has a representation like this, so that if you have X mu, then you can find some non-standard extension and an M finite set, which is called hyperfinite, that covers the image of your space, such that simultaneously for all integrable functions, the integral against the measure mu is equal to the standard part of this, computing the finite average as we described above. So what I'm going to describe is something similar to this. Well, so why do we want something? Why is this not enough? Well, maybe a reason is that the non-standard approach is non-constructive. So if you know the details of how it's set up, you use the axiom of choice a few times, and then to prove this theorem again, you use it not just in a countable form or something. So what this framework I'm going to talk about can be seen as is like a more constructive approach where things remain definable for the most part. And the main object is find filters so that, we're not necessarily going to have to use ultrafilters in order to do these things. Okay, by way of motivation, another reason this is valuable is, so here's a kind of explanation of why we might want infinitesimals to describe the size of sets. So suppose we have some space X, and then we have infinitely many subsets of it, AI, BI for I in the natural numbers. We can write a series of relations as follows. So this is saying like the size of AI is infinitesimal relative to the size of AI plus 1, and the size of BI is approximately Ri times the measure of AI, where Ri is a positive real number. So I don't include 0 because that would, you lose information there because you'd want to say, well, it's either, it's infinitesimal relative to it. So you'd want to include that information in the first kind of relation. Well, okay, so in this context that we're going to discuss, this has a relatively concrete meaning, and you can say, because these fine filters are going to be filters over the finite subsets of something, and this corresponds to statistical samples. So if you want to cache out what this means in terms of what you might observe, like with finitary data, you can say that a generic finite sample will have a typical finite sample of point Z will have for any I that you pick, you're going to have the ratio of the number of points that lie in Z and AI is to the number of points in AI plus 1 is smaller than any given 1 over n. And also the difference between the ratio of the Z intersect BI and Z intersect AI with the real RI is also very small. So this is kind of saying that, yeah, these things converge. So the idea being that there is a concrete meaning to these infinitesimals where the AIs, they're all very small, but they may, when you take more and more points, they may converge to 0 relative to each other at different rates. And I think this is a possibly useful way of talking about things because it can retain more information. So all these ideas of how fast these finite samples are converging to 0 relative to each other. This is lost if you just describe these with real valued measures because necessarily every one of them is converging to 0 in terms of real numbers. So you kind of lose all this fine-grained description if you forget about the infinitesimals. Okay, so on to the more technical things. So okay, so we introduced this notion, which is fairly natural once you read what it says, which is called a comparison ring. So this is what a comparison ring is: a commutative ring with unity, and it has a little bit extra structure. So it has this absolute value function, which we just take as a primitive, and a binary less than relation with the following properties. So first, less than is a strict partial order, so we don't assume it's a total order. 0 less than 1. We have number 3 is just the one of the axioms for ordered fields. So 4 is also 1, so the product of positive elements is positive. 5 says that the absolute value function is idempotent, and if you take the negative of something, then you get the same absolute value. For elements that are greater or equal to 0 in the disjunctive sense, the absolute value is already idempotent on them. You can kind of commute through absolute values. That's what 7 says. And there's a relation between the less, so 8 gives you a relation between the less than ordering and the absolute value, which is useful for making comparisons between things. And a key one, I mean, I think is the 9th, which is there's a condition for having a multiplicative inverse. So we say that an element, it has an inverse if and only if its absolute value is strictly greater than 0. So right, for ordered fields, you want to say every non-zero element has an inverse. We want every ordered field to be an example of a comparison ring, but in general, we're not going to be able to guarantee that things that we want to work with have a total order. So we need some the issue logically is that we need a kind of atomic formula that's equivalent to having a multiplicative inverse rather than the negation of an atomic formula, right? So in the ordered field context, says if it's not 0, then it has an inverse. And this gives you if its absolute value is greater than 0. Okay, so we'll see why that is important in just a second. But okay, so all of these are kind of things that elementary school children know about computing with real numbers, and so I think they should all be very intuitive. They suffice to carry out kind of ordinary computations that are used in proofs about these integrals that we'll introduce. Now, I spent some time to arrive at this set of axioms. I'm not sure if it's optimal, so I don't really know what I mean by that, but maybe it's something to consider, because we don't want it to be a complete set of axioms, because we want many examples that are not elementarily equivalent, because we want every ordered field to count as one of these rings. We don't necessarily want it to be real closed or something. So yeah, I don't know. Then there's a question of are the axioms redundant at all? I think they're not, but I haven't tried to check carefully. Okay, so some terminology here. So this is all standard terminology from, non-Archimedean fields, but they make sense in the context where they're not necessarily fields or totally ordered. So so comparison ring, let's say K is a comparison ring. Something is finite when its absolute value is less than a natural number in externally. So meaning you add one a finite number of times. Otherwise, it's infinite. We say that A is much less than B or infinitesimal relative to B if you multiply it by any integer, it's bounded between negative B and positive B.
Excuse me, can I ask a question here?
Yes.
Actually, on the previous slide, unless I missed something, there was nothing in this definition connecting the absolute values directly to the addition operation of the ring. Well, except for item 6, where it says that the additive identity is equal to its own absolute value. So I guess I'm probably overlooking something. I don't see why the finite elements are going to be closed under addition.
Because so we have axiom 2.
So the order is fine. But I see. Combine
so if
that.
you kind of inductively apply axiom 2 and axiom 3.
Yeah, if you use essentially axiom 3 ties the addition to the order, and then axiom 8 ties the order to the absolute value.
Yes.
And I can imagine the two. Okay, I think that answers my question. Thank
you. Yeah. Okay. Yeah. I mean, you can play around and see what basic corollaries there are, but yeah. So I think the expected things will follow, but unfortunately, I didn't give on the slides a kind of list of basic propositions. But okay, so let's go to we're here. So the next item was infinitesimal. Is when the absolute value of something is much less than 1. We say that A is approximately equal to B if the absolute value of the difference is infinitesimal relative to each one of them. And note that doing some algebra and cancellations, if A and B are invertible, then it's equivalent to saying that the ratio A over B or A times B inverse is infinitesimal. -1 is infinitesimal, so it's infinitely close to 1. And we say that two elements are Archimedean equivalent if they're they dominate each other by multiplying by natural numbers. Okay. So I'm not actually going to use all of these things, but they're kind of good definitions to know. Okay, so now we are getting into reduced powers. So this is a general model theoretic construction that we should all know. So for a structure A, just any first order structure and a set Z, let's say you have a filter F over Z, we will write power AF for the reduced power, which is, as we know, you take all functions from the set Z into A, and we say they're equivalent if they are equal on a set in F. And then we interpret the relations and functions in the reduced power according to the same criteria. So, right, if the relation holds, if it holds on a set in F, and that defines the interpretation of the language. Okay, if K is an ordered field, then usually the reduced power of an ordered field is not an ordered field, because if it's not an ultrafilter, we will be able to define some function which shows, I mean, we'll be able to define pairs of functions that are not comparable in order. So we'll lose the totality of the ordering and also the existence of inverses, because we can take a function which is 0 on a positive set and non-zero on a positive set, for example. But so modulo the filter is not equal to 0, but it's not invertible because it's not, it doesn't have an inverse on a positive set, right? But the important thing about why these axioms are introduced is that being a comparison ring is preserved under reduced powers. So this just amounts to checking each of these things. Most of them are pretty simple, but I mean, yeah. Well, I'll leave you to look at it if you don't believe me. But there's no difficulty there, really. This is I think there's some general work about the logical form of things that are preserved under reduced powers, and this may follow from this theorem, and I can't remember who it's due to, but it's from the 60s or 70s. But you can check it directly for this system of axioms. Okay, so for a comparison ring, we also have a notion of standard part, but unlike the case of ordered fields, there are kind of two standard parts. So there's kind of a lower and upper standard part. So you might have a member of the comparison ring that is bounded above by some rational numbers and below by some rationals, but those don't converge to the same point. So as an example, you can think of some function, like a function that oscillates, takes 0 on a positive set and 1 on a positive set. So the upper standard part would be 1 and the lower 0. But if they are equal, then we say the standard part is that common value. Right. Oh, and it could be in plus or minus infinity, right? If you can have infinitely large positive elements and infinitely negative elements too. Okay, so here's the definition of the integral. So what we do is, so the context is you have a divisible abelian group, so that taking a finite average makes sense. And you have a fine filter over a set x to the less than omega, so over the, so the elements of the filter are sets of finite subsets of x. And the integral is, you take a function f from the underlying set x to g, so not from the finite subsets of x, but from the underlying set. And then at each finite set, you just compute the average, and that gives you kind of the approximation of the integral at a point, let's say, or it's in terms of the filter, it's like the value at a point, and then you just take this modulo f. So this is kind of take an average of averages, and this easy to check has the expected, some of the expected algebraic properties of integrals. So at least for like when the underlying, the total measure of the space is 1. So if you take a single element, then and you integrate the constant function with that value, then you get this means the right, the function that assigns value c to every point in the space. And it's linear in the sense that the integral of the sum is the sum of the integrals. And if you can multiply, if there's a ring structure and it makes sense to take like c times f and d times g, then you also get that it's linear. And this just follows because it's at each point, it is linear like that, and we use abelianness to break them apart to get this equation. Okay, so and then there's this notation that I decided on for taking the standard part of an integral, which just makes it look a little bit nicer in the paper. And there's some LaTeX symbol where you can put a square in the integral, and I thought that was appropriate for standard part of an integral. And notice that the collection of functions which possess a standard integral, so meaning their upper and lower standard parts are equal, this is a vector space over Q, and then if the comparison ring you start with extends the reals or some subfield of the reals, then you can replace Q with R or that subfield. So meaning that, yeah, you can take linear combinations with those scalars. So, okay, let me try to go a little bit faster to get to the set theory eventually. So here's, I'll just state, this is a kind of the main combinatorial that allows us to build the kind of filters that we want in terms of representing different kinds of measures. So what this says is it's kind of an extension theorem, as lemma that says you can approximate the proportions of points lying in a given finite set as well as you want, and sort of meeting any finitely many criteria at the same time. So if you have a finitely additive measure, real measure, and you take finitely many measurable sets and finitely many points from the space and an arbitrary natural number, then you can take a finite set, Z, that satisfies the following properties. All of the points you want are in Z. So this is going to, when you're building your filter, you want to be able to witness fineness that way, so you can get any number of points into your given set. The set is much larger than the collection of points that you started with, so larger than n times L. And all of the points that are not demanded to be in Z, you can guarantee that they come from the given sets that you look at. If they have positive, if their union is positive. And importantly, the last thing is that we can get the proportion of points lying in one set to the other as closely as we want to the proportion of the measures. Okay, so this is a fairly straightforward thing to prove. I mean, it kind of is messy to write out the details, but you just kind of, the idea is, the key is that it gives measure 0 to all singletons. So whenever you have a set with positive measure, it's infinite. And so you can take as many points as you need from that set. Now, what you have to do is you take your given sets, you look at the positive ones, and you look at all the Boolean combinations of them. So you have a partition into things of positive measure, and then you kind of just select points, as many as you need to get those proportions close to the desired proportion of measures. That's the basic idea. Okay, so what does this imply? So the theorem, this is a in line with Henson's theorem. We have a representation theorem for finitely additive probability measures, and this says that if you have one of these mu, then you can define a filter f mu, a fine filter over x to the less than omega, which has this property that for all bounded mu measurable functions from x to the reals, their integral is equal to the standard integral of the function when you integrate against the filter instead of the measure. And in the countably additive case, we can allow unbounded integrable functions. So we can get this, there's one filter, there's a minimal one, definable from the measure, that gets all of this to happen simultaneously. The definition is quite simple. the key is just to verify that the desired collection of sets witnessing what you want to witness, it does have the finite intersection property, and that's where the lemma is used. And so a natural question is to ask, what exactly is this F mu? So this proposition characterizes that it's equivalent for a function in case of a countably additive complete probability measure, meaning all subsets of measure zero sets are measurable. If you have such a measure mu defined in the sigma algebra, then for a bounded function, it's equivalent that that f is measurable and it has the standard integral exists. So meaning that upper and lower standard part are equal. Okay, so these are the kind of representations that we can get in a kind of abstract way. I just want to say a little bit about the theory of iterated integrals, which is that it works well. The key reason that I wanted to work with this notion of comparison ring is that you take a reduced power and you get another algebraic structure where whatever you know about integrating functions with filters, taking values in comparison rings in general apply to doing that again. So we get a theory of iterated integrals that we can repeat any number of times. And so if you have two filters, then you can form the product filter in the usual way. And we can also think of it as a filter over the product of the two spaces. So in the case where you have fine filters, the usual thing is to think of, you have, set X, set Y, and you take the product. But here we have the collection of finite subsets. This is equivalent to, in terms of like the information, to taking a filter on the product of X and Y and taking the finite subsets, but only considering rectangles. And so we have the usual definition of the product filter, and this is basically like what does it say? That for along the y-axis, there's a set in the filter on which for every point there, the set along the x-axis, the cross section is in the filter for the x-axis. Okay, so we have the product filter, and it's a basic folklore fact that taking a reduced power of a structure with this kind of product filter is the same as iterating reduced powers in this sense, in this order that I wrote down there. And the integrals work out nicely in this case. So even for the just general setting of a divisible abelian group, if you have two fine filters, fg over x to the less than omega, y to the less than omega, respectively, then for all functions from x times y to the group k, the integral is equal in scare quotes, I should say, because you have to follow this canonical isomorphism. But it's following through in the isomorphism. It's the same as iterating the integral, meaning you, right, for every point in y, you would take the integral with this fixed point df, and then integrate that dg over the y coordinate. And that's the same result as if you just did this product integral. So, okay. All right. Any questions at this point? So, all right, now I want to focus on a kind of a particular example that I think is interesting, where some some set theoretic machinery comes in. So to motivate it, there's this well-known result that there's, in a sense, no analog of Lebesgue measure for infinite dimensional spaces. So, there, for infinite dimensional separable Banach space, there is no measure that such that every set is Borel, so meaning countably additive measure, making every Borel set measurable. The measure is translation invariant, and every point has a neighborhood with a finite measure. And the proof is that you can show that if X is an infinite dimensional normed vector space over the reals, then every open ball contains an infinite collection of pairwise disjoint open balls of equal radius. So if the measure was translation invariant, they would all have to have the same measure. But if you can, right, the third point says that you should be able to take a small enough ball that's of finite measure, and then you can take these infinitely many things that are of equal finite measure. But that's a contradiction, right? Because they sum to infinity. So, right, this even contradicts finite additivity. If we additionally assume that every open ball of finite radius has a positive real measure, you could kind of weaken the assumption if you assume things are countably additive. So the construction I'm going to give gives an interesting contrast to this. So going to non-Archimedean measures instead of ones with real values. This screen is not changing. Okay, there we go. We are able to get something that has most of these features. So what is the space? What we're going to look at is what I call R to the less than omega, which we'll define as omega sequences of real numbers that are eventually zero. So this is just a kind of direct limit of the Rn's, which can be represented as just, Rn is the set of all real sequences that are equal to zero after place M, or that's, yeah, after place N. And of course, this is a real vector space, it has a Euclidean norm, exploiting the fact that the vectors are eventually zero. And let me introduce a weird definition that will be, the relevance of this is regarding open balls, because the impossibility result is about these open balls in normed vector spaces of infinite dimension. So for an integer n, let mu n be the Lebesgue measure on R to the n. And let's call a set middling if for all but finitely many n, it's Lebesgue measurable, and it has measure less than infinity. And for infinitely many n, it's a positive measure. So the idea is that these sets are, they're not too large because they have finite intersection in terms of measure with finite measure intersection with almost all n. But for infinitely many, it's still positive, so it's not finite dimensional. Every open ball is going to be middling, because if you just intersect an open ball in R to the less than omega with Rn, that's just an open ball in Rn. Okay, so the theorem is that we have a filter gamma on this space over R to the less than omega to the less than omega, so the finite subsets of it, with the following properties. So there's an increasing sequence of infinitesimals. Sorry, I kind of started talking too fast, but here we go. So there's a infinite sequence of infinitesimals that are of increasing Archimedean class, such that, so let's set M of A just be the integral of the characteristic function of A. It has the following properties. So epsilon n is the value that's given to the n-dimensional unit cube. And then what we have to do that takes a little bit of care is that this respects the surface volume in terms of geometry. So for every, so I didn't define this, but so if you, so we know what n-dimensional surface in Rm is. So you have, it has a parameterization in n dimensions, and there's a map that is from an open set subset of Rn into some possibly larger R to the m, right? And then we can consider subsets of that, like any Borel subset. And because of the theorem about the measure of surfaces being invariant under change of coordinates, it's well defined to talk about the Lebesgue measure of Borel subsets of arbitrary surfaces that are presented in this way. So what we have is actually we have an algebra of surface fragments. So Borel subsets of things that are parameterized in this smooth way. And I didn't write down the definitions, but we are considering, maps that are C1. I mean, this is the standard theory of smooth surfaces, so that everything works out as expected. So what happens for these is that the measure of, according to this non-Archimedean measure of a set A that's a Borel subset of a surface, is its n-dimensional volume times this this factor epsilon n, which is the size of the n-dimensional unit cube. So, and then plus a delta, which is infinitesimal relative to that. So the idea is that it has the expected volume, maybe plus some error that is of lower dimension. And countable subsets are, according to this filter, very small. So they all get a measure smaller than the one-dimensional unit cube, unit line segment. And for the middling sets, so these are the ones that are larger than every finite dimensional set, but not too large, then the measure is actually translation invariant approximately on them. So meaning that if you translate by any vector, you get the measure is almost equal in the sense that when you take the ratio, it's infinitesimally close to 1. Okay, so I won't talk about the proof of this, but you have to, it uses this lemma that I talked about before. You sort of have to step up inductively through dimensions and make sure that the points that you're picking kind of don't destroy the ratios you set up in smaller dimensions. So now I want to, this is more of a kind of philosophical point, but there's this thing called the Borel-Kolmogorov paradox, and this is so slow I'm sharing screen from a different device and it isn't going through the Zoom very fast. Okay, well, I'll talk over this change of screen. So what this is a kind of paradox about probability that comes from considering probability distribution on the sphere and looking at kind of conditional probabilities of circles or great circles on the sphere. So let's talk about, what does this say? This presentation, so I wanted to give a picture, is due to Kenny Iswaran. So, okay, so you have a sphere and you consider a small circular region around the pole. So this region here. And so it's a circular region, so you have this symmetry. And what we want to ask is, let's say we know that we're on a great circle. So we have the bottom of the sphere here. It doesn't really matter. We want to ask, if we know we're on a great circle, what is the probability that that we're in this set? So let's say this is A, and this great circle is C. What is the probability of A given C? Well, intuitively, it should be the same as the probability of A. So, or let's say the probability of A given S. The reason is because it's symmetrical. It should be that the chance that you land, if you know that you're on this great circle, land in A, it's the same as if you know that you're just on the sphere. What's the probability that you land in A? Well, this is an inconsistent intuition. So why is this? If you revolve the sphere around a perpendicular axis, you get this band, right? So imagine the red part revolving around. So it traces out this band. And now look at a great circle that goes to this perpendicular axis. So another picture over here. So we have this band and a great circle going from here to here. Now the proportion of, so we want to ask what is, so this is another set B, which is larger. Let's give it a different color. So here's B. So again, the intuition should be that the probability of landing in B, given that you're in, let's call this D, this great circle, given that you're in D, should be the probability of B given that you're in the sphere. Okay, what's the problem? Well, the proportion of arc length on D, well, the key is there's a common great circle. So there exists a single thing. There's a C star that is a great circle connecting these two poles, right? And so the probability of being in, I mean, it's the same, the intersection B intersect C star is just the same set as A intersects C star. So these conditional probabilities are going to be the same if you substitute C star for either C or D, but B is clearly of larger surface area than A. So we have a contradiction. So this is one presentation of this paradox. So here's the conclusion, right? The measure of A over S is the same as this, but it's the same as B over S, but we cancel things out. Measure A equals measure B. This is false. Now, okay, again, the thing needs to speed up. Give it a second. Any questions about the picture I drew? Wow, okay, it's going really slow. Are you guys seeing my pen right now? Okay, this happened like,
it was lagging behind what you were saying. So
okay.
Yeah.
Maybe next time I should connect the iPad directly to Zoom. I didn't experience this before. maybe it's, I don't know, yeah. Okay, here's the next slide. So, okay, so we have this contradiction. Now, if we replace the equal sign with approximately equals, we still have the same contradiction. So if we sort of carry out the same reasoning, but we say, you know, these things should be equal up to infinitesimal, and we know that the proportion of A to S is not infinitesimally close to the proportion of B to S, which it shouldn't be according to the standard geometry, we still arrive at the same problematic conclusion. So, okay, that seems to pose a problem for non-Archimedean kind of reasoning, perhaps. What did Kolmogorov say about this? He said, the problem is that we tried to condition on a measure zero event, and that's just not allowed. And that's in a sense, that's a good answer because, you know, we have a working mathematical theory for conditional probabilities when we don't do that. But it looks like, you know, if we're in a situation where we can divide by infinitesimally small things because, you know, we're in an algebraic structure where that makes sense, then we kind of still arrive at a similar paradoxical conclusion. Now, I mean, there's another part of the argument where we can say it's an error, and I think it's clearly this, you know, I kind of hinted at it when I said should be, to kind of give a scare sign around the equal sign, which is that we said, oh, because of considerations of symmetry, the chance of lying in A, given that you're on the great circle, for some reason should be the same as the probability of lying in A, just given that you're on the sphere. But I think this, you know, this is where the argument is lacking some justification. So let me kind of skip over this because I'll go through it quickly. Iswaran gives a kind of a reason bolstering why this should be, you know, is valid, and his argument is, well, he gives a name to a principle he calls conglomerability, and this says that in a situation, well, the considerations of symmetry kind of should give you an equation that justifies this conclusion. So it's kind of argued by analogy, where if you have a set B that's partitioned into finitely many pieces, then you can compute the probability of B by doing this kind of sum of conditional probabilities weighted on the probabilities of each partition. And he says that this should generalize to the infinite case and give you an integral equation which justifies this. The idea in this case would be that here we had this conditional probability, the probability of lying in, let's say, the set B, and the AIs could be like different great circles. By considerations of symmetry, each of those conditional probabilities inside the integral should be the same. And so we should be integrating like a constant times, you know, against the measure, and then we'd get the desired equation. But so what makes this not valid is a kind of failure of additivity, where, you know, it just follows from finite additivity, but at some point when you have a partition of the space into uncountably many pieces, we know that the integral equation is not necessarily going to hold. So what I want to say is that we do have this one notion of integration that kind of respects surface areas in different dimensions, and in our case, we would say the conditional probability of being on this segment of the arc is you know, its classical length compared to the classical length of the arc. That's what the integral in terms of the filter will give you. So both of these are given some non-zero but infinitesimal value in this general comparison ring. And the conditional probability you can define as the probability of the intersection divided by the probability of the set you're conditioning on. And in our situation, Kolmogorov's objection doesn't apply because, it makes perfect sense to divide by infinitesimals in our situation. We're not dividing by 0. So anyway, this is kind of the philosophical portion of this talk that, okay, there are competing intuitions, and I think that the geometric intuition about this, that's the picture given by the integral, which respects classical volumes in different dimensions in some sense, is compelling enough, and we should go for that over this integral equation. Okay, now I'm almost out of time. I'm sorry, well, depending on your opinion of what the time should be, but I want to talk about something a bit more set theoretical and maybe skip some details.
Monroe,
So,
you have
yeah,
a bunch of time, no worries.
okay,
Yeah, I mean, you have a half an hour at least, so take your time.
okay. So let's go ahead and go at a normal pace through this last part. Okay, so we have this filter on r to the less than omega, which respects classical notion of geometrical dimension. So let me let the slide catch up to me. Well, the question is, okay, there are as we know, other notions of dimension that go beyond the integer dimensions. There's Hausdorff dimension, various other approaches to kind of generalizing dimensions. And for example, Hausdorff dimension, you can, within Rn, you can find sets of any real dimension, less between 0 and n, for example. This slide is not moving. Okay, so what I'd like to explore is a similar kind of extension of dimension that is suggested by these kinds of integrals. So what we had was a sequence of infinitesimals where objects that are n-dimensional are given some value in this comparison ring, which is proportional to the n-dimensional unit object according to their classical volume. So, and then the objects of larger dimension are of a different Archimedean class than the ones of smaller dimensions. So the smaller ones are infinitesimal relative to the larger ones. So a natural question would be, what about things of, are there sets that have Archimedean class in between some of these dimensions? And furthermore, what is the global structure in terms of the ordering of these dimensions look like? So I'm going to give a kind of partial answer to those vague questions, but you'll see, that there's clearly more to say when I get to what I can say. So here's the definition I want to work with. Suppose you have a fine filter f over a set of the form x to the less than omega. Let's let dimension sub f of a set A denote the Archimedean class of the integral of the characteristic function of A. So far this is according with the filter gamma over r to the less than omega, and which accords with the classical notion of dimension of smooth surfaces. So we say that something that's of smaller dimension, A is smaller dimension than B, when the integral of its characteristic function is infinitesimal relative to that for B. Now, note the following feature. If you take a filter F and you enlarge it to a bigger filter, you're still going to have you're going to preserve the ordering of the dimensions. And the reason is the statement that characteristic function of A integral is infinitesimal relative to B is witnessed by a set of so a sequence of assertions that saying certain sets are in the filter, meaning for each natural number n, we say that the collection of Z such that the proportion of elements that get into A versus get into B is going to be smaller than 1 over n. So we have the set of Z's with this property is in the filter for each n. So if you extend to a bigger filter, that's going to be true for the larger filter. So these dimensions are preserved in terms of the comparison between them as you pass to larger dimensions. So another notion is useful for the construction, which is I say that a set is F solid if it is of larger Archimedean class or a larger dimension than any countable set. So by the construction of the filter gamma, every set that every smooth surface of positive volume or a Borel subset of it of positive measure is solid in this sense, because we made sure that all the countable sets were infinitesimal relative to the unit line segment. So, can everyone still hear me? My computer is saying something funny.
Yes, we can hear you, yes, but we can't see what you are writing.
Okay. Oh, I did write something which will come
It will
very
appear
slowly.
at some point in the future.
Yeah, sorry. I was just writing down this the sets which were in the filter.
Right.
Yeah, there it goes. Asserting that A is infinitesimal relative to B. So you have this omega collection of different sets that you say are in the filter in order to make this assertion. Okay. So I'm going to go on to the next slide. So the next lemma is where we are actually using some kind of standard set theoretic techniques. And what I'm giving you is a construction of filters on sets of size omega 1. And so far I can't say anything interesting in more general situation, but we'll see in the course of the sketch of the proof why I stick to omega 1. I mean, the basic explanation is kind of that the filters they're fine filters, so they have to do with talking about what happens on finite sets. Okay, countable sets are approximated by finite sets, and omega 1 is approximated by countable sets. So we're able to sort of step up that far, but not beyond. So we'll see how that kind of plays a role in the argument in a second, as soon as the slow computer decides to follow along. So any questions while we wait? Even questions about why are you doing things this way, or why is that interesting? Okay, well, here's the slide. So here's the lemma. Suppose you have a filter over omega 1 to the less than omega that is generated by a base of size omega 1. So the hypothesis applies to the filter gamma if we assume CH. Because if you look at the, well, okay, so look at the conclusion of what we assert the filter to do. We said that for all Borel sets, blah, blah, blah happens. And so for each, single Borel set or pair of Borel sets, depending on what your assertion you're checking, you have an assertion that some set is in the filter. So you can just look at the collection of all sets that need to be in the filter to make these assertions true. And that's going to be omega 1 many things. I mean, the heart of the proof is just checking that each thing that you want the filter to do, collectively, when you put them all together, you have the finite intersection property so that it is indeed a filter. So that's why the hypothesis is relevant. So suppose also we have two omega 1 sized collections of subsets of omega 1. The sets A alpha are supposed to be are smaller than the sets B alpha. Each B alpha we assume is F solid, and as I just said, the dimension of A alpha is less than dimension of B beta for each alpha beta. Then we can extend to a larger filter F prime, still with a base of size omega 1, and find a F prime solid set C that fits in between, that kind of fills the gap. So, so dimension, according to F prime of C, is larger than each A alpha and smaller than each B beta. Okay. So, yes, so let's do this. Let's go through the argument. So fix enumerations for things. So the filter has a base of size omega 1, enumerate that. Fix a surjection from omega 1 to the finite subsets of omega 1, such that each thing is repeated many times. And then take a continuous chain of countable elementary submodels of H omega 2 of length omega 1, where it's an epsilon chain, and assume that these objects that we just described are in the smallest model, M0. Okay. I'm just waiting for the screen to change, but of course this is a standard setup of an argument for some kind of construction on omega 1. I have thought a little bit about, trying to carry out certain similar constructions, maybe in the presence of some forcing axioms, but I didn't make any progress that was worth mentioning yet. But there's probably something to do in that direction. So on the next screen change, I'll try to anticipate the time a little bit better. Touch it before. This is really taking a long time. Has anyone experienced this before with Zoom?
No, it's a very weird thing.
Yeah.
So you can see the screen, the new screen on your tablet or whatever it is.
Yeah.
Or that it's just not mirroring it. Very strange. Yeah, I don't know what the problem is.
Let me start by describing the idea in a way that maybe depends less on seeing the things written, and then we'll see them written. So, so the idea is you work sort of over M0 first. You have the sets A alpha and B alpha that are indexed by ordinals less than, here we are, less than M0 intersect omega 1, right? So, okay, we know this is a countable set, this M0 intersect omega 1. So we can enumerate all of its ordinals in an omega sequence. And what we do is we build an omega sequence of finite sets with the following property, right? So each Zn0 is a finite subset of this countable ordinal M0 intersect omega 1. It's in, Zn is in, it's in something in the filter. So it's in the intersection of the sets X alpha, where X alpha is an index coming from pi of Xi0n, where so pi is this surjection from omega 1 to the finite subsets of omega 1, right? And we wanted to have the following properties. So when you get to stage n, we know that each A alpha is infinitely smaller than each B alpha. So for each n, we can witness this in the sense that there is this Z0n with the property that its intersection with A alpha is as small as we want in proportion to the intersection with B beta. So where alpha and beta are two ordinals coming from this finite set that is given to us by the enumeration. We want to make the proportion different enough so we square n, multiply by 2, and multiply by the number of things that we have. Okay, and then we want these Zn's to grow fast enough. So that's what the clause 4 says. So they're at least doubling in size. Their intersection with each B beta is at least twice as big as the entire previous Zn that we selected. Okay, so this is our sequence of finite sets, and so they're eventually going to, the union is going to be all of M0 intersect omega 1, and because of fineness, because eventually you're going to hit each ordinal below there, and in X alphas, at some point you're going to be forced to include any given ordinal below that point. So then we choose our first approximation to this C that's supposed to fit in between all the A alphas and the B alphas. So we choose a set C0 contained in M0 intersect omega 1, such that for each n, Zn intersect C0 is and each alpha in pi Xi n, the set C is going to be n times as large intersected with Zn as A alpha is, and then B beta is n times as large intersection with C as that ratio is also n, and that's why we squared n in clause 3, right? So how do you do that? Well, you build C0 inductively, choosing the thing satisfying the desired inequalities using 3, and you use 4 to make sure that when you go to n+1, you are sort of not disturbing the proportions that you set up for n. So when you pick sets to be in C0 intersects Zn+1, don't make them come from well, you can pick them from points in the B betas that have not been previously considered. So you just don't want to Z intersect, right? Sorry, it's written right there. D n+1 intersect Zn is just Dn. So they stabilize. Okay, this is the idea, and so we basically continue this. We continue doing the same thing in each step. So we will kind of be taken care of automatically at limit steps by kind of continuity of the process. But when we get to a successor step, this is where the assumption of solidity comes in. And so recall that we assumed all the B alphas are solid. That means that they are of larger dimension than any countable set. And in particular, so it's still waiting to go to the next page, but so in particular, let's say you get to a successor, a model indexed by a successor ordinal. So the previous model is a member of this model you're working on now. And so it knows that the previous model is countable. And what you want to do is you select, let's say you're at alpha and alpha plus 1, and you're building your set C sub alpha plus 1. C sub alpha plus 1 intersect the model M alpha should be the same as C alpha intersect M alpha. And because M alpha is countable and this next model knows that, it knows that we can, when we're adding these, when we're picking our points to build the set C alpha plus 1, we don't need to ever choose them from M alpha because that's going to be infinitesimally small compared to the B betas that we're working with. Still not moving. Okay. So this is the idea of the construction. So so again, conceptually, we're doing an omega stage induction at each step, right? And that's enabled by the fact that the model is actually countable. So we're sort of given the model and we enumerate it externally and build something. And then, but we do this omega 1 many times. Okay, there we are. And the idea is that the previous stuff that we've done can be seen to all be very, it's countable from the point of view of the next step. Okay, so in the end, so I just kind of vaguely described this, but this is all written here. And right. Each B gamma is solid. Right, this is basically what I said. Okay. Okay, so in the end, right, you have that you're going to preserve this inductive hypothesis, which is the second bullet point there. And you set C just to be equal to the union of all the C alphas. And so C alpha intersect M alpha is going to be, or C intersect M alpha is going to be C alpha. And in the end, you've taken care of everything you need to take care of, right? The idea is, okay, now consider two arbitrary finite subsets of omega 1. This gives you a finite subset of the A alphas and the B betas. And we want to check that the set that we built C lies in between them. Well, eventually you've gotten to a point where this initial segment of C you've taken enough points to witness that it's much larger. So in terms of some arbitrary n, it's like n times as large as the sum of the cardinalities of all the A alphas, right? There is some finite set Z that's going to be in your filter that has its intersection with C is n times larger than all of these and n times smaller than each of the B betas. And then we just write down the sets that we need to witness all of this, and we find that what we have has the finite intersection property and it's generated by a base of size omega 1. So I've already talked past the next slide. But this is the idea for creating the set C. Okay, now I'll just go to the theorem at the end, which if you buy the lemma, you can see what we're going to do for the theorem. I'm gonna just reshare because this is lagging way too long. Let me do this again. Or yeah. Okay, so here's the last slide, which is this is the theorem about what we can say about the structure of these dimensions. So if we assume that GCH holds on the first two infinite cardinals, then we have the following. We can extend this filter gamma, which is a definable thing, to an ultrafilter in omega-2 many steps. So we apply the lemma omega-2 many times. And each step we generate a larger and larger filter with a base of size omega-1 so that we can continue. And we end up getting the following. So now we're in ultrafilter. So when you take an ultra power of the rationals, so recall that the measure of a set is this kind of filter limit of rational numbers, right? Which is finite sets intersected a set with the size of that finite set. So it's going to be linearly ordered, so the dimensions are comparable. Okay, so we want to ask what kind of order properties does this linear order have? Well, it has the property that there aren't any omega-1 gaps or omega-1 omega gaps, because we set it up so that if you take two omega-1 sized collections of sets, where the dimension of everything in T is larger than the dimension of everything in S, then at some point we constructed in the induction a set that sits in between the S and the T. And so consequently, right, if we take any interval of dimensions, it has neither a cofinal or solid dimensions. So we have to assume the large ones are solid. So if we have an interval of solid dimensions, then it doesn't have a cofinal or a co-initial set of size omega-1. Okay, so this tells you something about the structure. At least there exists an ultrafilter giving you this structure of dimensions, which is a quite different kind of linear order from Hausdorff dimension, of course, which is indexed by the reals. Okay, so that's all I wanted to say. Thanks for your attention. Obviously, there are many directions you could go with this, and I hope some of you found this somewhat interesting, and maybe you have some ideas about how to move beyond the GCH case in this construction. So thanks.
All right, Monroe, thanks very much for the super interesting talk. Questions for Monroe? Anyone?
Oh, I'll ask Monroe, I like your notation. I mean, I don't really get everything, but is this like in the future students might learn this in calculus class?
I mean, I would hope so, but who knows? I think it's a relatively elementary concept, and the notation seems natural to me. So yeah, I would hope it could be taught to calculus students.
Great, thanks.
Anyone else? All right, Monroe. Oh,
A sort of naive question. I don't know if it's right. Early on, you were doing the sort of iterated integrals. How do the how do the rectangular filters sort of sit inside the collection of filters as a whole, or fine filters? Or, does that make sense to ask?
Like compare it to all possible
Yeah, compared
filters on the product space.
right.
Yeah, I mean, I don't know. I mean, it's a restricted class of
Right.
things. There are going to be many filters that don't concentrate on rectangles. Yeah.
Right. That's, I don't know. It doesn't make sense to ask how restrictive or.
Yeah, I don't know. I wouldn't know how to quantify that at this point.
Yeah. Thanks. Interesting talk.
Thanks.
All right, anyone else? Okay, Monroe, thanks very much again.
Thank
Yeah,
you.
thank you.
What do we have next week?
Philip Welch is speaking.
Oh, Philip is speaking.
Oh,
Okay. Okay, and I already have his title and abstract. Okay, good.